name is Rosemary Rose. Thank you so much for joining me. I'd like you to get somewhere comfortable, somewhere you can relax. And I am going to help bore you to sleep with a math lecture. Linear algebra, vector spaces. Linear algebra is the study of linear maps on finite dimensional vector spaces. Eventually, we will learn what all these terms mean. For now, we will define vector spaces and discuss their elementary properties. In linear algebra, better theorems and more insight emerge if complex numbers are investigated along with real numbers. Thus, we will begin by introducing complex numbers and their basic properties. We will generalize the examples of a plane and of ordinary space R to the n and C to the n, which we then will generalize to the notion of a vector space. As we will see, a vector space is a set with operations of additional and scalar multiplication that satisfy natural algebraic properties. Then our next topic will be subspaces, which play a role for vector spaces analogous to the role played by subsets for sets. Finally, we will look at sums of subspaces analogous to unions of subsets and direct sums of subspaces analogous to unions of disjoint sets. Complex numbers. You should already be familiar with basic properties of the set R of real numbers. Complex numbers were invented so that we can take square roots of negative numbers. The idea is to assume we have a square root of -1, denoted by I, that obeys the usual rules of arithmetic. Here are the formal definitions. A complex number is an ordered pair, AB, where A and B are within R, but we will write this as A plus BI. The set of all complex numbers is denoted by C. C equals A plus BI, or A and B within R. Addition and multiplication on C are defined by A plus BI plus C plus DI equals A plus C plus B plus DI, or A plus BI times C plus DI equals AC minus BD plus AD plus BC times I, where A, B, C, and D are within R, the real numbers. If A is within R, we identify A plus 0I with the real number A. Thus we think of R as a subset of C. We usually write 0 plus BI just as BI, and we usually write 0 plus 1I as just I. To motivate the definition of complex multiplication given above, pretend that we knew that I squared equals -1, and then use the usual rules of arithmetic to derive the formula above for the product of two complex numbers. Then use that formula to verify that we indeed have I squared equals -1. The symbol I was first used to denote the square root of -1 by Euler in 1777. Do not memorize the formula for the product of two complex numbers. You can always rederive it by recalling that I squared equals -1, and then using the usual rules of arithmetic. The next example illustrates this procedure. The product 2 plus 3i times 4 plus 5i can be evaluated by applying the distributive and commutative properties. 2 plus 3i times 4 plus 5i equals 2 times 4 plus 5i plus 3i times 4 plus 5i becomes 2 times 4 plus 2 times 5i plus 3i times 4 plus 3i times 5i becomes 8 plus 10i plus 12i minus 15 becomes -7 plus 22i. Our first result states that complex addition and complex multiplication have the familiar properties that we expect. The properties of complex arithmetic being commutativity, alpha plus beta equals beta plus alpha, and alpha times beta equals beta times alpha for all alpha and beta within C, the complex numbers. Associativity, alpha plus beta plus lambda equals alpha plus beta plus lambda, and alpha times beta times lambda equals alpha times beta times lambda for all A, B, and lambda within C, the complex numbers. Identities. Lambda plus 0 equals lambda, and lambda times 1 equals lambda for all lambda within C, the complex numbers. Additive inverse. For every alpha within C, the complex numbers, there exists a unique B within C, such that alpha plus B equals 0. Multiplicative inverse. For every alpha within C, the complex numbers, with alpha not equaling 0, there exists a unique beta within C, such that alpha times beta equals 1. The distributive property lambda times alpha plus beta equals lambda times alpha plus lambda times beta for all lambda, alpha, and beta within C, the complex numbers. The properties above are proved using the familiar properties of real numbers and the definitions of complex addition and multiplication. The next example shows how commutativity of complex multiplication is proved. Proofs of the other properties are left as exercises. To show that alpha times beta equals beta times alpha for all alpha and beta within C, the complex numbers. Suppose alpha equals A plus BI and beta equals C plus DI, where A, B, C, and D are within R, the real numbers. Then the definition of multiplication of complex numbers shows that alpha times beta equals A plus BI times C plus DI becomes AC minus BD plus AD plus BC times I, and beta times alpha equals C plus DI times A plus BI becomes CA minus DB plus CB plus DA times I. The equations and the commutativity of multiplication and addition of real numbers show that alpha times beta equals beta times alpha. Next, we define the additive and multiplicative inverses of complex numbers, and then use those inverses to define subtraction and division operations with complex numbers. Definition: negative alpha, subtraction, 1 over alpha, division. Suppose alpha and beta are within C, the complex numbers. Let negative alpha denote the additive inverse of alpha. Thus, negative alpha is the unique complex number such that alpha plus negative alpha equals 0. Subtraction on C is defined by beta minus alpha equals beta plus negative alpha. For all alpha not equaling 0, let 1 divided by alpha and 1 over alpha denote the multiplicative inverse of alpha. Thus, 1 over alpha is the unique complex number, such that alpha times 1 over alpha equals 1. For all alpha not equaling 0, division by alpha is defined by beta over alpha equals beta times 1 over alpha, so that we can conveniently make definitions and prove theorems that apply to both real and complex numbers. We adopt the following notation. F stands for either R, the real numbers, or C, the complex numbers. The letter F is used because R and C are examples of what are called fields. Thus, if we prove a theorem involving F, we will know that it holds when F is replaced with R, and when F is replaced with C. Elements of F are called scalars. The word scalar, which is just another word for number, is often used when we want to emphasize that an object is a number as opposed to a vector. For alpha within F and M a positive integer, we define alpha to the M to denote the product of alpha with itself M times. So alpha to the M equals alpha times alpha times alpha times alpha M times. This definition implies that alpha to the M to the N equals alpha to the M times N, and alpha times beta to the M equals alpha to the M times beta to the M. For all alpha and beta within F and all positive integers M and N. Before defining R to the N and C to the N, we look at two important examples. The set R squared, which you can think of as a plane, is the set of all ordered pairs of real numbers. R squared equals x and y such that x and y are within R. The set R3, which you can think of as ordinary space is the set of all ordered triples of real numbers. R cubed equals x, y, and z, such that x, y, and z are within R. To generalize R to the second and R to the third to higher dimensions, we first need to discuss the concept of lists. Suppose n is a non-negative integer. A list of length n is an ordered collection of n elements, which might be numbers, other lists, or more abstract objects. Two lists are equal if and only if they have the same length and the same elements in the same order. Many mathematicians call a list of length n an n-tuple. Lists are often written as elements separated by commas and surrounded by parentheses. Thus, a list of length 2 is an ordered pair that might be written as A, B. A list of length 3 is an ordered triple that might be written as X, Y, Z. A list of length n might look like this: Z1, Z2, Z3, Z4, up until Zn. Sometimes we use the word list without specifying its length. Remember, however, that by definition, each list has a finite length that is a non-negative integer. Thus, an object that looks like x1, x2, and so forth, which might be said to have infinite length, is not a list. A list of length 0 looks like empty brackets. We consider such an object to be a list so that some of our theorems will not have trivial exceptions. Lists differ from finite sets in two ways. In lists, order matters and repetitions have meaning. In sets, order and repetitions are irrelevant. The lists 3-5 and 5-3 in parentheses are not equal, but the sets 3-5 and 5-3 in brackets are equal. The lists 4-4 and 4-4-4 in parentheses are not equal. they do not have the same length, although the sets 4, 4 and 4, 4, 4 in brackets both equal the set 4 in brackets. To define the higher dimensional analogues of r to the 2 and r to the 3, we will simply replace r with f, which equals r or c, and replace the 2 or 3 with an arbitrary positive integer. F to the n is the set of all lists of length n of elements of f. F to the n equals x1, x2, x3, x4, and so on to xn, such that xk is within f for all k equals 1, 2, 3, 4, and so on to n for x1, x2, x3, x4, and so on to xn within f to the n, and k is within 1, 2, 3, 4, and so on to n. We say that xk is the kth coordinate of x1, x2, x3, x4, and so on until xn. If f equals r and n equals 2 or 3, then the definition of f to the n agrees with our previous notions of r to the 2 and r to the 3. C to the 4 is the set of all lists of 4 complex numbers. C to the 4 equals z1, z2, z3, z4, such that z1, z2, z3, and z4 are within C. If n is greater than or equal to 4, we cannot visualize r to the n as a physical object. Similarly, C to the 1 can be thought of as a plane, but for n greater than or equal to 2, the human brain cannot provide a full image of C to the n. However, even if n is large, we can perform algebraic manipulations in f to the n as easily as in r to the 2 or r to the 3. For example, addition in f to the n is defined as follows. Addition in f to the n is defined by adding corresponding coordinates x to the 1, x to the 2, x to the 3, x to the 4, and so on to x to the n plus y to the 1 plus y to the 2 plus y to the 3 plus y to the 4, and so on until y to the n equals x to the 1 plus y to the 1, x to the 2 plus y to the 2, x to the 3 plus y to the 3, x to the 4 plus y to the 4, and so on until x to the n plus y to the n. Often the mathematics of f to the n becomes cleaner if we use a single letter to denote a list of n numbers without explicitly writing the coordinates. For example, the next result is stated with x and y in f to the n, even though the proof requires the more cumbersome notation of x1, x2, x3, x4, and so on through xn, and y1, y2, y3, y4, and so on until yn. If x and y are within f to the n, then x plus y equals y plus x. Proof. Suppose x equals x1, x2, x3, x4, and so on until xn is within f to the n, and y equals y1, y2, y3, y4, and so on until yn are within f to the n, then x plus y equals x1, x2, x3, x4, and so on through xn, plus y1, y2, y3, y4, and so on through yn equals x1 plus y1, x2 plus y2, x3 plus y3, x4 plus y4, and so on through xn plus yn becomes y1 plus x1, y2 plus x2, y3 plus x3, y4 plus x4, and so on through yn plus xn becomes y1, y2, y3, y4, and so on through yn plus x1, x2, x3, x4, and so on through xn becomes y plus x, where the second and fourth equalities above hold because of the definition of addition in f to the n, and the third equality holds because of the universal commutativity of addition in f. If a single letter is used to denote an element of f to the n, then the same letter with appropriate subscripts is often used when coordinates must be displayed. For example, if x is within f to the n, then letting x equal x1, x2, x3, x4, and so on through xn is good notation. Even better, work with just x and avoid explicit coordinates when possible. Let 0 denote the list of length n, whose coordinates are all 0. 0 equals 0. Here we are using the symbol 0 in two different ways. On the left side of the equation, the 0 denotes a list of length n, which is an element of f to the n. Whereas on the right side, each 0 denotes a number. This potentially confusing practice actually causes no problems because the context should always make clear which 0 is intended. Consider the statement that 0 is an additive identity for f to the n. X plus 0 equals x for all x within f to the n. Here, the 0 above is the list defined, not the number 0, because we have not defined the sum of an element of f to the n, namely x, and the number 0. A picture can aid our intuition. we will draw pictures in R2 because we can sketch this space on two-dimensional surfaces such as paper and computer screens. A typical element of R2 is a point V equals A, B. Sometimes we think of V not as a point, but as an arrow starting at the origin and ending at AB. When we think of an element of R2 as an arrow, we refer to it as a vector. When we think of vectors in R2 as arrows, we can move an arrow parallel to itself, not changing its length or direction, and still think of it as the same vector. With that viewpoint, you will often gain better understanding by dispensing with the coordinate axes and the explicit coordinates and just thinking of the vector. The two arrows have the same length and same direction, so we think of them as the same vector. Mathematical models of the economy can have thousands of variables, say x1 through x5000, which means that we must work in R to the 5000. Such a space cannot be dealt with geometrically. However, the algebraic approach works well. Thus, our subject is called linear algebra. Whenever we use pictures in R2 or use the somewhat vague language of points and vectors, remember that these are just aids to our understanding, not substitutes for the actual mathematics that we will develop. Although we cannot draw good pictures in high-dimensional spaces, the elements of these spaces are as rigorously defined as elements of R2. For example, 2, -3, 17, pi, square root of 2 is an element of R5, and we may casually refer to it as a point in R5 or a vector in R5 without worrying about whether the geometry of R5 has any physical meaning. Recall that we defined the sum of two elements of f to the n to be the element of f to the n obtained by adding corresponding coordinates. As we will now see, addition has a simple geometric interpretation in the special case of R2. Suppose we have two vectors, u and v, in R2 that we want to add. Move the vector v parallel to itself so that its initial point coincides with the end point of the vector u. The sum u plus v then equals the vector whose initial point equals the initial point of u and whose end point equals the end point of the vector v. In the next definition, the 0 on the right side of the equation is the list 0 within f to the n. For x within f to the n, the additive inverse of x, denoted by negative x, is the vector negative x within f to the n, such that x plus negative x equals 0. Thus, if x equals x1, x2, x3, x4, and so on through xn, then negative x equals negative x1, negative x2, negative x3, negative x4, and so on through negative xn. The additive inverse of a vector in R2 is the vector with the same length but pointing in the opposite direction. We illustrate this way of thinking about the additive inverse in R2. As you can see, the vector negative x has the same length as the vector x, but points in the opposite direction. Having dealt with addition in f to the n, we now turn to multiplication. We could define a multiplication in f to the n in a similar fashion, starting with 2 elements of f to the n and getting another element of f to the n by multiplying corresponding coordinates. Experience shows that this definition is not useful for our purposes. Another type of multiplication, called scalar multiplication, will be central to our subject. Specifically, we need to define what it means to multiply an element of f to the n by an element of f. The product of a number lambda and a vector in Fn is computed by multiplying each coordinate of the vector by lambda. Lambda times x1, x2, x3, x4, and so on to xn equals lambda x1, lambda x2, lambda x3, lambda x4, and so on through lambda xn. Here, lambda is within f, and x1, x2, x3, x4 through xn is within Fn. Scalar multiplication in Fn multiplies together a scalar and a vector, getting a vector. In contrast, the dot product in R2 or R3 multiplies together two vectors and gets a scalar. Scalar multiplication has a nice geometric interpretation in R2. If lambda is greater than 0 and x is within R2, then lambda x is the vector that points in the same direction as x and whose length is lambda times the length of x. In other words, to get lambda x, we shrink or stretch x by a factor of lambda, depending on whether lambda is less than 1 or lambda is greater than 1. If lambda is less than 0 and x is within R2, then lambda x is the vector that points in the direction opposite to that of x and whose length is the absolute value of lambda times the length of x. A field is a set containing at least two distinct elements called 0 and 1, along with operations of addition and multiplication, satisfying all properties. Thus, R and C are fields, as is the set of rational numbers, along with the usual operations of addition and multiplication. Another example of a field is the set 0, 1 in brackets, with the usual operations of addition and multiplication, except that 1 plus 1 is defined to equal 0. In this book, we will not deal with fields other than R and C. However, many of the definitions, theorems, and proofs in linear algebra that work for the fields R and C also work without change for arbitrary fields. If you prefer to do so, throughout much of this, you can think of F as denoting an arbitrary field instead of R or C. For results that have as a hypothesis that is F is C, you can probably replace that hypothesis with the hypothesis that F is an algebraically closed field, which means that every non-constant polynomial with coefficients in F has a 0. A few results require the hypothesis of on F that 1 plus 1 does not equal 0. The motivation for the definition of a vector space comes from properties of addition and scalar multiplication in Fn. Addition is commutative, associative and has an identity. Every element has an additive inverse. Scalar multiplication is associative. Scalar multiplication by 1 acts as expected. Addition and scalar multiplication are connected by distributive properties. We will define a vector space to be a set V with an addition and a scalar multiplication on V that satisfy the properties in the paragraph above. An addition on a set V is a function that assigns an element U plus V within V to each pair of elements U, V within V. A scalar multiplication on a set V is a function that assigns an element lambda V within V to each lambda within F and each V within V. Now we are ready to give the formal definition of a vector space. A vector space is a set V along with an addition on V and a scalar multiplication on V such that the following properties hold. Commutativity. U plus V equals V plus U for all U and V within V. Associativity. U plus V plus W equals U plus V plus W, and A times B times V equals A times B times V for all U, V, and W within V, and for all A, B within F. Additive identity. There exists an element 0 within V such that V plus 0 equals V for all V within V. Additive inverse. For every V within V, there exists W within V such that V plus W equals 0. Multiplicative identity. 1 times V equals V for all V within V. Distributive properties. A times U plus V equals A times U plus A times V, and A plus B times V equals A times V plus B times V for all A, B within F and all U, V within V. The following geometric language sometimes aids our intuition. Elements of a vector space are called vectors or points. The scalar multiplication in a vector space depends on f. Thus, when we need to be precise, we will say that V is a vector space over f, instead of saying simply that V is a vector space. For example, R to the n is a vector space over R, and C to the n is a vector space over C. A vector space over R is called a real vector space. A vector space over C is called a complex vector space. Usually, the choice of F is either clear from the context or irrelevant. Thus, we often assume that F is lurking in the background without specifically mentioning it. With the usual operations of addition and scalar multiplication, f to the n is a vector space over f, as you should verify. The example of f to the n motivated our definition of vector space. The simplest vector space is 0, which contains only one point. F to infinity is defined to be the set of all sequences of elements of f. F to infinity equals x1, x2, x3, x4, and so on, such that xk is within f, for k equals 1, 2, 3, 4, and so on. Addition and scalar multiplication of f to infinity are defined as expected. x1, x2, x3, x4, and so on, plus y1, y2, y3, y4, and so on, equals x1 plus y1, x2 plus y2, x3 plus y3, x4 plus y4, and so on. Lambda times x1, x2, x3, x4, and so on equals lambda x1, lambda x2, lambda x3, lambda x4, and so on. With these definitions, f to infinity becomes a vector space over f, as you should verify. The additive identity in this vector space is the sequence of all zeros. Our next example of a vector space involves a set of functions. If S is a set, then f to the s denotes the set of functions from s to f. For f and g within f to the s, the sum f plus g within f to the s is the function defined by f plus g times x equals f to the x plus g to the x. For all x within S. For lambda within f and f within f to the s, the product lambda f within f to the s is the function defined by lambda f times x equals lambda f of x for all x within S. As an example of this notation, if S is the interval 0, 1 and f equals r, then r 0, 1 is the set of real valued functions on the interval 0, 1. You should verify all 3 bullet points in the next episode, in the next example. If S is a non-empty set, then f to the s with the operations of addition and scalar multiplication as defined above is a vector space over f. The additive identity of f to the s is the function 0 such that s goes to f, defined by 0 of x equals 0. For all x within S. For f within f to the s, the additive inverse of f is the function negative f such that s goes to f, defined by negative f of x equals negative f of x for all x within S. Alright, my lovelies, it is time for you to go to bed now. Good night. Pleasant dreams.